scholars, and today we're going to check out velocity and acceleration. So let's go ahead and warm it up by thinking about the circle that's given by the vector valued function r at t is cosine omega t times I plus sine omega t times j. So what we're going to do is we're going to use a graphing calculator in parametric mode to graph this circle for several values of omega. All right, so let's check it out. So let's go ahead and take a look at a space curve. And we're going to have a times t. A will be our omega. So right at 0, we have none of the circles sketched. Does that make sense? So we haven't created any of this circle. We have this vector here, and the vector is just the I vector, right? Because cosine at 0 is going to be 1. So you would just get I, 1 times I. So this is what it starts out with. It's 0. Now let's go ahead and let's see what happens as A increases, right? As A increases. So when A keeps going here, so now A is at about a half, and do you see how it's almost halfway? So looking down there, I've changed the view just a little bit, but here we've got A is halfway there, or A is at a half, and we've made a semicircle. Now let's take a look as we go to 0.75 for omega. Oops. And you'll see it's 3/4 of the way around, right? And then I think you can kind of get the gist of what's going on. And then when omega RA here is 1, we get all the way around 1 revolution of the circle. Good so far? As we keep going, what's happening is it's made a second revolution around the circle. Okay, so now let's take a look at what happens as we move t. So here, what we get to look at here, do you see is, increase it here. So what we're looking at is, do you see at the blue arrow, that's the terminal point of the vector, okay? Terminal point of the vector. And then we've got, as t goes backwards, it's going like this. So let's just animate and see if this graph, if the speed is changing at all right? So I'm going to just animate it. And do you see that it's at a constant speed? Isn't that cool? So basically what's happening is the black vector is our tangent vector to this parametric vector valued function. Okay, so remember that here, let's zoom in on these just so we can make sure you can see them. This was when omega was equal to 0. So we ended up just with a vector I, right? And then when we let omega equal to 1/2, we ended up with halfway around the circle here, right? And when we ended up with, when omega was equal to 3/4 or 0.75, it was 3/4 of our circle. And then here, when omega was 1, it was a full circle. And it traced one time. Now, if omega was 2, it would trace around twice. Okay? So now, what's happening as omega increases? As omega increases, what's going to happen? The velocity of the terminal point increases. So remember, on each of these, we had, can't see it that well, let's go to this one. So here, this right here would be our terminal point. So that would be our terminal point. Is right here. Cool? And this vector here, is our vector valued function, r, at t. And in this case, it was equal to cosine 1t, right, because omega was 1, times I, plus sine 1t times j. And then I just zeroed out the k vector. Cool, cool? Now, this one here, is our velocity vector. Velocity vector at time t. And so that's sort of a big picture of what we have going on. Now, coming back down here, how does omega affect the velocity of the terminal point as it traces out the curve? Well, remember, I think we already answered that. Just move this down here. As omega increases, the velocity of the terminal point increases. And for a given value of omega, does the speed appear constant? Well, yes, it didn't increase the speed, right? Now, what about the acceleration? Would it be constant? I don't think so, right? Because since there's a change in direction, there should be a change in acceleration, right? So just kind of ponder that for a few minutes and see how that goes. I love that grapher. It's very cool. Okay, so now let's look at the definitions of velocity and acceleration. So if x and y are twice differentiable functions of t, because remember, acceleration is the second derivative of some position function. And r is a vector valued function given by r at t, is equal to x at ti plus y at tj, then the velocity vector, acceleration vector, and speed at time t are as follows. So our velocity vector is going to be denoted v at t, and that's just equal to r prime at t, and that in turn is what? Beautiful. It would be x prime at t times I plus y prime at t times j. Good so far? Awesome. Now the acceleration vector is going to be denoted by a at t. So a at t will equal to r double prime at t, or the first derivative of the velocity vector, right? Which would equal to x double prime at t times I plus y double prime at t times j. Now the speed is just the magnitude of the velocity vector, which would be the magnitude of r prime at t, which in turn would be what? The square root of x prime at t squared plus y prime at t squared. Cool, cool? Now, for motion along a space curve, that's all planar, right? For motion along a space curve, the definitions are as follows. Well, we're just going to add on a k there and a z at t function. So, what's velocity going to be? V at t would be, again, r prime at t, which would be x prime at t times I plus y prime at t times j plus z prime at t times k. The acceleration, a at t, is r double prime at t, which would be x double prime at t I plus y double prime at t times j, and plus z double prime at t times k. And again, the speed is going to be the magnitude of v at t. I should have written v at t over here. Which would be the magnitude of r prime at t, which would be the square root of x prime at t, the quantity squared, plus y prime at t, the quantity squared, plus z prime at t, the quantity squared. Cool, cool? All right, so let's look at an example. The position vector r at t equal to 3 cosine t times I plus 2 sine t times j describes the path of an object moving in the xy plane. Sketch a graph of the path and sketch the velocity and acceleration vectors at the point 3, 0. So here, let's take a look. If x is equal to 3 cosine at t and y is equal to 2 times sine at t, and we know what? Cosine squared t plus sine squared t has to be 1, right? So if I isolate cosine t, that would mean that x over 3 squared, which is cosine t squared, plus the sine squared t would have to equal to 1, right? So that just gives us x squared over 3 squared plus y squared over 2 squared is 1. Now, let's take a look at our graph and sketch our acceleration vectors. So here, this, I'm sure you remember, is going to be an ellipse with its major axis horizontal. So So what it will look like will be something like that. Probably have it a little too pointed at the ends. But now we need to figure out its orientation, right? So let's check this out. We'll do the orientation in a different color. So at t equal to 0, what do we get? Well, x would equal to 3 times cosine 0, so that would be 3, and y would equal to 2 times sine at 0, which would be 2 times 0, which is 0. So we know that it starts at 0, 3. Now, how about at t equal to pi over 2? X is now going to zero out, right? And y is going to be 2. So we know that it's moving in this direction. And it's going to complete one revolution in 2 pi. Make sense? Okay, so now let's take a look at our vectors. So here are our velocity vector is going to be, remember, r prime at t, which is, let's see, -3 sine at t times I plus 2 cosine at t times j. And now our v at 0 is going to be 0i plus 2j, so just 2j. But remember, at t equal to 0 wasn't x3, so it would start here, and it would go, and it would terminate. It would terminate at the point 3, 2. That makes sense? So this is v at 0. How about v at pi over 2? So v at pi over 2 would be, I think we get a positive 3i. So it would start here, right, at our x and y coordinates at 0, 2, and it would go over here to terminate at -3 at -3, 0. That makes sense? Let me draw that a little better because I think I went too far. Okay, And so this was v at pi over 2. Cool so far? Now let's look at the acceleration vector. So our acceleration vector, we would just take the derivative of r prime at t, right? So a at t is going to be r double prime at t, which will be -3 cosine t times I minus 2 sine t times j. So a at 0 would be -3i plus 0j. So remember, it would start here and then it's going to go this way, so along the axis. So this would be acceleration at time 0. And then let's do acceleration at pi over 2. So that would end up giving us 0i and then minus 2j. So at pi over 2 we start here and then we would go down this way. So this one would be a at pi over 2. Cool, cool? Now, what do you notice about these? It turns out your velocity and acceleration vectors at a given value of your parameter are going to be orthogonal. Cool, cool? Perpendicular. Okay, so I think we did all of that because we found the velocity acceleration vectors at the point 3, 0. We went a little beyond. We also did it at another point, but we're all good. Okay, so now, next example, the position vector r at t equal to t squared times I plus t times j plus 2 times t to the 3/2 times k describes the path of an object moving in space. We want to find the velocity, speed, and acceleration of the object. So v at t, remember, is r prime at t, which is beautiful 2ti plus 1j plus 3/2 times 2 is just going to be 3. So we'll have 3t to the 1/2 times k. Cool so far? So that's our velocity vector. Our acceleration vector, a at t, remember, is r double prime at t. So that's going to give us, beautiful, 2i. J is going to zero out, and then we'll get plus 3/2 t to the -1/2 times k. All right, and then the speed, remember, it's going to be the magnitude of v at t. So that's going to be the square root of, so we'll go back to the first one, 2t, the quantity squared, plus 1 squared, plus 3t to the 1/2 squared. And so that's going to be the square root of 4t squared plus 1 plus 9t. And if we put it in descending order, descending powers of t, we'll have 4t squared plus 9t plus 1. All right, very good. Okay, next up, position function for a projectile. So, neglecting air resistance, the path of a projectile launched from an initial height h with an initial speed v0 and an angle of elevation theta is described by the vector function r at t is equal to v0 cosine theta times times t, and then I, plus h plus v0 sine theta times t minus 1/2 g for gravity times t squared, and that's times j, where g is the gravitational constant. Now, it depends on what unit you're in. G is 32 feet per second squared, or G is 9.8 meters per second squared. So let's take a look at this next example. Determine the maximum height and range of a projectile fired up at a height of 3 feet above the ground with an initial velocity of 900 feet per second and at an angle of 45 degrees above the horizontal. So let's see what we've been given, okay? We'll make a little bit of a list here. So we know that h is 3, and we know that we're in feet, right? 3 feet. And what else have we been given? Initial velocity. So v0 is our initial velocity, and it is 900 feet per second. Theta was 45 degrees. And since we're in feet, g is going to be equal to 32 feet per second squared. Cool, cool? All right. So let's see what we have going on. We have here, we have this projectile. So that's a little better. Okay. So here we go. We know that in general, r at t is equal to, because we just got this formula, so v0 times cosine theta ti plus h plus v0 sine theta times t minus 1/2 times g times t squared, and that's all the coefficient to the j. Cool so far? All right. So what we want to find out, if this is, let's say, we start out here at 3 feet. Which would probably, you'd barely even be able to see it. It probably goes very, very high. But basically, you start very near the origin here, and you're going off at a 45-degree angle from where you start. So you're going to go something like this, and then you want to know where this projectile, it'll hit the ground at some point, right? So that's where it would, hit the ground right here, and it's going to have some kind of max height somewhere around here. We would get our max height. okay? And then basically we took a look here. This was 3 feet, and this right here, our angle theta, was 45 degrees from that. Groovy? Okay, so let's see what we get when we plug all our stuff in. So r at t, plugging our information in, is 900 from our initial velocity times cosine 45 degrees, that times t I, plus our height was 3 feet, plus 900 times sine 45 degrees times t, minus 1/2 times 32 for g, t squared. And that's all with j. Cool so far? Okay, so let's find out what we have going on. We can simplify r a bit. So then that would be 900 times root 2 over 2 t times I, plus 3 plus 900 times root 2 over 2 times t, minus 16 t squared. That's times j. Okay, so r at t will then be 450 root 2 t I, plus negative 16 t squared plus 450 root 2 t plus 3, and that's times j. So here we are looking for if we look at that horizontal tangent vector, right, we're thinking about the tangent vector where we get that max height, right? So here the max height we'll actually find by setting y prime at t equal to 0. So y prime at t in general is going to be what? So remember, the y prime is the coefficient to our j, right? So it's going to be d dt of negative 16t squared plus 450 root 2t plus 3. And that, of course, will be negative 32t plus 450 root 2. Cool so far? Now, setting that equal to 0, we would have 32t is equal to 450 root 2 times t. No, just 450 root 2. So to get t, I divide 450 root 2 by, I'll keep it as a fraction right now. Sometimes it's good to keep it as a fraction until you're ready to finish. So the max height occurs when t is equal to this here, which you can definitely take out a 2, right? So we would get 225 root 2 over 16 in seconds. Okay, that's when it occurs. The time it occurs, but we want what the max height is. So we need to evaluate y. Add another page here. So we need to evaluate y at 225 root 2 over 16 to find what that maximum height is. So we found the time when it happens, but not what the height was yet. So let's figure it out. It's going to be 3 plus 450 root 2 times 225 root 2 over 16 because that's what I'm plugging in for t, and then minus 16 times 225 root 2 over 16, the quantity squared. So this is coming from what our y at t is, okay, which was right here, this coefficient to the j is what our y at t is. And n for t, we're plugging in 225 root 2 over 16. Cool? All right, so it turns out when you approximate this, you're going to get approximately 6,331.125 feet. Okay, and that will be our maximum height. And it occurs at time 225 root 2 over 16 seconds. Groovy? Now, to find the max range, okay, so for the max range, what do we need to do? Well, this time we need to set y at t equal to 0. So again, y at t was equal to 3 plus 450 root 2 t minus 16 t squared. And so if I set that equal to 0, I'll put it down in descending order. So we'll have negative 16t squared plus 450 root 2t, and then plus 3. I'm just using x for the symbol. It's really t. We want to find the zeros, right? Okay, so it looks like our zero occurs at approximately 39.779 seconds, right? And this is the graph for just y, not the whole thing, of course, because it's just y at t. But we wanted to know when y at t was equal to 0, all right? We found out the time that happens. The time that it happened was at time approximately t is 39.779. And now which part do you think we plug it into to find out how far it goes? It's on the horizontal. So now if we go back to x at t, right? And x at t, remember, was 450 root 2t was equal to 450 times root 2t was x at t. And so x at 39.779 is going to be approximately, well, I'll show how I'm plugging it in. So equals 450, again it's approximate, root t times 39.779. So that's going to be about 25,315.500 feet. And that will be the max range of the projectile. Cool? So let me make sure. So max range was this, okay? We had to find the t where that happened, so we let y at t equal 0 to do that. And the max height ended up being 6,331.125 feet, approximately, and that occurred when the derivative of y at t was 0, and that happened when t was 225 root 2 over 16 seconds. Okay, so now let's take a look at the next one. A baseball is hit from a height of 2.5 feet above the ground with an initial velocity of 140 feet per second and at an angle of 22 degrees above the horizontal. Use a graphing utility to graph the path of the ball and determine whether it will clear a 10-foot high fence located 370 feet from home plate. So let's see what we've got. We've got our H is 2.5, and that's in feet. G, therefore, will be 32 feet per second squared. Theta is 22 degrees. And our V0, our initial velocity, was what, 140 feet per second. Cool? Okay. So let's see what we've got. Our x at t is going to be equal to 140, because that's our V0, times cosine theta, which was 22 degrees, times t. Our y at t is equal to 2.5, right, the initial height, plus 140, initial velocity, times sine at 22 degrees, times t, minus 1/2 times 32t squared. Cool so far? So, what do they want us to answer, right? Let's go ahead and use the parametric form to graph this. So I'm going to go into parametric, and we want to make sure that we're in degrees. So mode, degrees, and then parametric, done. So now when I do my y equals, I've got x at t and y of t. So what was x at t? We had 140 cosine 22 t, and then y at t was 2.5 plus 140 times sine 22 times t and then minus, it'll be 16t squared. All right, so let's just take a look. All right, so let's trace the graph and get to where we're at 10. Okay? So we're trying to get to where y is 10, so it's a little low. Okay, it's a little under 10 right there. And that happens when x is 406. So if x is 375 feet from home plate? Feet from home plate, which is what this is depicting. That's almost that. Y is like 20 feet, so it's definitely going to clear it. So as we were saying, we've got our values here. Our values here for when x is almost 375, and it's on its downward run, and it's still way up at 20 feet. So we can definitely, it didn't ask us for anything exact, but we can definitely say yes. At approximately 375 feet, y is approximately 20.5 feet. And the ball, it is descending. Cool? Okay. All right, so example 5, that'll be our last one. Find the maximum speed of a point on the circumference of an automobile tire of radius 1 foot when the auto's traveling 55 miles per hour. Compare this speed with the speed of the auto. So we're going to use the following formula for the cycloid. R at t is b times omega t minus sine omega t times I plus b times 1 minus cosine omega t times j. Omega is the constant angular velocity of the circle, and b is the radius of the circle. So here we go. V at t is going to be what? Remember, it's going to be r prime at t, and that would end up being equal to b omega minus b omega cosine omega t. Cool so far? And that's, of course, just times I. And then we'll have, I'll leave the b out this time, so we'll have b times sine, actually it'll be omega sine omega t times j. Cool? So, cleaning it up a little, v at t would be b times omega 1 minus cosine omega t times I plus b omega and then sine omega t times j. And then, of course, you could factor out a complete omega from that at b omega if you wanted. And then we would just get 1 minus cosine omega t I, and then plus sine omega t j. Good, good? Okay, now the speed, remember, is the magnitude of v at t. So that's going to end up being the absolute value of b omega, because they're constants, times the square root of 1 minus cosine omega t squared plus sine omega t squared. So then we'll get the angular velocity should be positive, and the radius is positive, so we can just call this b omega, and then we'll get the square root of 1 minus 2 times cosine omega, 2 times cosine omega t plus cosine squared omega t plus sine squared omega t. And that's nice because isn't that just equal to 1? So we'll get b times omega times the square root of, that would be 1 plus 1 is 2, and then we'll have, we can factor that out because it'd be 2 minus 2 cosine omega t, so then we need 1 minus cosine omega t. So then we would get root 2 b times omega times the square root of 1 minus cosine omega t. Cool so far? Now, when is the maximum value going to occur? What do you think? Well, just think about it. If cosine at 0, would be 1, so you'd have 1 minus 1, which is 0. But cosine at pi, right? If omega t was equal to pi, wouldn't you get 1 minus negative 1? So you'd get 2 in there. So the max value occurs when omega t is pi. And then what would you get? So that would give us root 2 b omega root 2, right? Which of course is 2 times b omega. So this is when the max value is going to occur. So we're going to just hold on to this. We'll use it in a while, okay? So now let's just take a look at getting the 55 miles per hour into feet per second. So we're moving on to that. So 55 miles per hour, 1 hour, right, times 5,280 feet per 1 mile times 1 hour per 3,600 seconds. So that's going to give us approximately 80.67 feet per second. Feet per second. Cool so far? Remember that r was equal to 1. We were given that r was 1 in the problem. and velocity is equal to r times omega. So the max speed of a point on the tire is going to be two times b times omega. That's from this over here, which remember was the max value of the speed of a point on the tire. Okay, and so since the radius is equal to 1, this would end up being 2 times 1 times 80.67, right, from over here. And that ends up being 161.34, and that's in feet per second, which gives us approximately 110 miles per hour. So, just to recap, right here, what I highlighted in green is when the max value occurs when our omega t is pi, right? And we ended up getting 2 times b times omega. So velocity is r omega, right? This part right here. Double the velocity, since b is equal to r, is going to be the max speed of a point on the tire. Okay? And that's what we got for our result. Groovy? All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe. Bye.